I like to argue for multiple roles for V1, motivated by the attentional bottleneck that makes us inattentionally blind. The standard model of V1 sees V1 as more or less passive, outside the more important and complex tasks for vision. Most ideas about V1 ignores the information bottleneck. We perceive only a tiny fraction of visual inputs, mainly the inputs within the attentional spotlight. This spotlight is selected mainly by a gaze shift. This visual location was in the peripheral visual field before the gaze shift. I have proposed that a saliency map is created in V1. The hotspots in this map attract gaze shifts exogenously. Therefore, peripheral V1 computes saliency to guide attention. It motivates the idea that the bottleneck starts right after V1. The bottleneck makes the information impoverished, so that recognition can be ambiguous. Even in central vision, one may be uncertain, for example, whether this is a red flower or a red apple. More recently, I proposed that central vision can send a feedback to query for additional information, particularly from V1, to resolve the ambiguity. This is as if to look up information from the blackboard. However, I hypothesize that this happens only in central vision due to limited brain resources. So there's a functional difference between central and peripheral vision. Therefore, central V1 is for recognition, which is helped by the recurrent feedback query. The bottleneck motivates both the V1 saliency hypothesis and the central-peripheral dichotomy theory. A diagnostic type of information lost downstream from V1 is the information about the eye of origin of visual inputs. This information is invisible to perception. Human observers cannot tell whether visual inputs are shown to the left eye or the right eye. But this information is available in V1, which has many molecular neurons tuned to this information. But this information is lost in V2 and further downstream areas because they have only binocular neurons. A convincing evidence for the saliency map comes exactly from this eye of origin feature for saliency. In this image, human observers are asked to quickly find a uniquely oriented bar. This is an example when all these bars are shown to the left eye only. If one background bar is shown to the right eye instead, the perceived image is unchanged. This bar, unique in eye of origin, is not distinctive at all to perception. However, in most trials, the first saccade is directed to this non-distinctive bar, before saccading to the search target. This is as if this non-distinctive bar has a unique color, but only V1 is not colorblind. This behavior is a fingerprint of V1 for saliency and has been replicated by other labs. Another evidence comes from an experiment in which a monkey tries to find an uniquely tilted bar to saccade to it as quickly as possible. Meanwhile, we record from V1 neurons responding to the target bar. This plots the neural responses versus the time since the bars appear before the monkey makes the saccade. This is the average response from trials with a faster onset of the saccade. This is from trials with slower or incorrect saccades for the same visual input. Their difference should therefore be associated with the saliency difference in behavior. This difference is significant at a very short latency of 40 to 60 milliseconds, too short for the saliency signal to arise from feedback from any downstream visual regions. Evidence for the CPD theory includes many illusions that are only visible in peripheral vision. Here is an example. You see illusory motion in a static image, but not at where you fixate your gaze. Your peripheral vision lacks the feedback to look up the V1 blackboard, so can be easily fooled by information-impoverished feed-forward signals. Central vision is not fooled because it has the feedback query to verify feed-forward signals. We predict a new illusion, the reversed depth illusion. This is illustrated by a 3D depth difference between a disk in front of a ray. Both depth surfaces are covered by random black and white dots. This scene is depicted by a random dot stereogram, giving a veridical perception of the disk in front of the ray. The reverse depth illusion arises when we revise this stereogram to give an anti-correlated random dot stereogram, in which, for the disk, each black dot in one eye corresponds to a white dot in the other eye. Such a disk is nonsensical. But V1 neurons tuned to depth are fooled. They respond as if the disk is behind the ring. In other words, these V1 neurons report to higher brain areas that the disk is behind the ring. Central vision does not get fooled. It sees the disk as neither in front nor behind. But peripheral vision sees this reversed depth illusion reported by V1 neurons as theoretically predicted. A second prediction naturally follows. This reverse depth illusion should become visible in central vision when the feedback query is impaired, so that central vision also cannot query the V1 blackboard to veto the fake news reported by these depth-tuned V1 neurons. This prediction is confirmed. The feedback is compromised using a visual psychophysics trick of backward masking, which quickly removes the original visual inputs to make them unavailable for the feedback query. This backward masking is achieved by making the random dot stereogram dynamic, with a very short interval between successive frames of the dynamic stereogram. Therefore, V1 has multiple roles in vision. It creates the saliency map to guide attention. It starts information bottleneck, and is a critical player in the feed-forward feedback network for visual recognition in light of the bottleneck. This framework provides a fresh perspective on how vision works. In feeding forward information for visual recognition, it resembles the standard model of V1, but adds that the feed-forward information is massively limited by the bottleneck. Its feedback query can be related to the idea of V1 as a blackboard or high-resolution buffer. However, our feedback query is motivated by the presence of the bottleneck. Additionally, this feedback query is only or mainly for the central visual field. The feedback is to query for additional information through the bottleneck in order to help the particular ongoing recognition, using the algorithm of analysis by synthesis. This feedback is not for predictive coding. This framework has provided highly non-trivial and falsifiable predictions, some of which are already confirmed by data. Current and additional predictions provide further opportunities to falsify or revise this framework. So far, it has withstood the substantial test of time.